This is Unit 10, Section 10.3, chi-squared, continuing now doing a test of homogeneity. And so that, I always thought that word was kind of a funny word to say, and I like to make Siri or Alexa say it because they're like homogeneity. I don't know why, but it makes me laugh. So I'll share that with you. All right, so we have done our chi-squared distributions, our goodness of fit test, and that's where we are now comparing and doing multiple proportions tests at one time. The chi-squared test for homogeneity, okay, we're going to spend 2 days on, and then I'll show you the chi-squared test for independence, which is very much related to the homogeneity test. So as we continue in this unit, we are still doing a test that considers now many chi-squared goodness of fit tests at once for multiple independent samples of two-way table data. So this is where when we do chi-squared goodness of fit, hello S's, okay, this is one list. And so we're going to compare one list to a claimed distribution. So we looked at M&Ms and their distribution, we looked at a die and its distribution, and then we had practice on one list ideas. The chi-squared test of homogeneity, okay, is now going to be multiple chi-squared goodness of fit tests all at once. And so it's going to now create a two-way table of data where we have two different populations asking about categorical variables. So this could be something that we're going to ask, okay, if you fall into juniors with brown hair, those are going to give us those two ideas there and give us the two columns. Okay, what's your hair color is going to be one question, and then what's your grade level is going to be the other question, creating this two-way table of information. We still have the conditions, and they're the same as the chi-squared goodness of fit, random, independent, and large counts, where all the expected counts are at least 5. We have a new way of counting or finding our expected values. So this is one way that it differs from our goodness of fit to the homogeneity. Now we're going to have a row total times a column total all over the table total, or I say total total. And so we'll calculate those expected values, and I'll show you how to find that on our calculator. Our chi-squared statistic is still the same calculation, observed minus expected squared out of the expected. So we still have to find the chi-squared test statistic that tells us if it's pretty small, that's going to be our sampling variability. If it's really big, that's going to be different from what the distribution has been claimed to be. And so the last part that's different, this one's the same, is our degrees of freedom. Instead of doing number of categories minus 1, now we take the number of rows minus 1 times the number of columns minus 1. So I'll show you how to do this similarly on our calculator as well. So we have a couple differences of what we did with goodness of fit, where we had one list compared to a claim. Now we're going to have a two-way table with multiple numbers in it that are going to be compared all at once. So we're kind of building up to this idea where we started with one proportion, then we went to 2 proportions. Chi-squared goodness of fit is several proportions. Chi-squared test for homogeneity is several goodness of fit tests, so several distributions. And so that's where it gets really interesting, and some of the more realistic data that's a little bit messier. So I kind of like that. All right, so here's an example kind of starting us off. It says, does the background music influence wine choice? So marketing researchers for BevMo suspects that the type of background music that is played in their store might affect the type of wine that customers purchase. They designed and carried out an experiment where they had no background music playing, a French accordion music playing, and an Italian string music playing in 3 randomly selected stores, and recorded the number of French, Italian, and other kind of bottles of wines that were sold. The results are provided in the table below. Notice that this is no longer just one list. This is now we have 3 lists if we're looking at the wine type, 3 lists looking at our music type. This is our two-way table where we add music type and wine type. And so this goes back to Unit 4 where we did lots of probabilities as far as what's the probability I would pick somebody that listened to no music at all. 84 out of 243. What's the probability that we randomly select somebody that was listening to accordion music and ordered French wine? 39 out of 243. So we have those ideas of overlapping and bringing back that two-way table. So the first thing that we want to do is calculate the expected values. And so the way that we do that is we take our row total times the column total and then divide by the table total. So in each one of these, we need to calculate that value. So the French, we're going to take the 99 row total times 84 column total and divide by total 243. I cracked myself up, I'm telling you. All right, so when I do that, I get 34.22. Never round your expected up to an observed value, so we leave it as that rounded value. It's okay if you go 34.2, but don't round to an observation. I'm going to do the same thing here. 99 times 75 divided by 243. And here, 99 times 84 divided by 243. And then to my next row, 31 times 84 divided by 243. 31 times 75 divided by 243. 31 times 84 divided by 243. So I'm just keep going. 113 times 84 divided by 243. And 113 times 75, still that same idea here. And last one, 113 times 84, we still get that 39.06. So those two columns end up being the same because they had the same total in them. All right, so now we have our expected counts. And so even though we observed 243, we didn't expect each one of these to be evenly divided. We expected to see 30. We observed 30, we expected 34. Okay, that's a little different. We observed 11, we expected 10.7. That's closer than this one. We observed 1, we expected almost 10. Okay, that's getting a little bit more different. So if there was no association here, we would expect that those would all be evenly kind of distributed amongst the proportion of music type and wine type here. So when we're finding this is our expected counts. This is what would happen if there was no influence from the music to the wine, that they can play anything or nothing, and it shouldn't influence what was being selected here. On the next part, it says, okay, is there convincing evidence that the background music type influences the type of wine that is purchased at the store? Convincing evidence. That means we're running a test. So let me show you how we're going to do that first step of our 4-step process here. We don't want to define, holy moly, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 different variables. That is not what we're going to do. We're kind of going to, similar to our chi-squared goodness of fit, we define our variables and talk about the context in the hypothesis. So the way that we talk about a chi-squared test of homogeneity is we're going to say there is, and then this phrase, no difference. Okay, there's no difference in the distribution of music type and wine type. We're just saying in this case, there's no difference. It should all be the same. And so that's where when we do chi-squared goodness of fit, we say the distribution matches the claim. This is that same idea. We're saying, okay, they're not being influenced together. There's no difference between them. It doesn't matter music type to wine type. There should be no difference there. And so then when we want to come up with our competing or alternative hypothesis, this is when we're going to say there is a difference in the distributions. So we have to write out a little bit here in our hypothesis, but we don't have to define all 9 different combinations of music type and wine type because we're talking about them as their distributions here. So it's a little bit different for our state part, and we still have an alpha that we would say, if not given to us, we'll take 0.05, and that will give us our entire state. We don't have to define 9 variables. We kind of define that context in our hypothesis. So then the step 2, what's our plan to test these? This is where we're going to go into the chi-squared test for independence. Sorry, for homogeneity. So we're doing a chi-squared test because we have a 2-way table, not just one proportion, not just one list. And then this is for homogeneity. And so we have that idea of homogeneous where it's saying that they're all the same, they're very similar, and then we would have our alternative is that there's a difference between them. So that's kind of that connection here. There's no difference between them, they're all the same, versus there is a difference, they're not the same. Just like we did for our chi-squared goodness of fit, we'll check our conditions. Were these randomly selected or randomly assigned? And so as I'm turning back, we're looking at randomly selected here. So that's condition is met. 10%, okay, well we had 243 participants. I'm guessing that in there, if this is a large restaurant chain here, we would have time, or we would have more than 2,000 customers, but we might not have the time to do that, but it's possible. And then large counts. Okay, so this is where we look at our expected, which we just calculated here. And again, make sure we're looking at the expected values, because if we looked up here, the condition says that in order to proceed with a chi-squared distribution, we need it to have all expected values bigger than 5. If you look up here, you might say, oh, it fails because of the 1. That's not what we're looking at. We're looking here. None of my values are below 5. I expect at least 5 in every category. So we would say all expected counts are greater than or equal to 5. So that meets our condition. Now we're ready to go to our calculator and actually find what is our chi-squared test statistic and what is the p-value associated with it so that we can make our conclusion. Is there a difference or is there no difference in these distributions? So when we go to our calculator, we're ready to run a test. And so I'm going to go to test. I'm going to scroll up. Here's goodness of fit where we had a list of values. The other option we have is a chi-squared test. So when I select this, notice that it's not asking for a list. This is now asking us to pull up our observed and expected matrices. And so we have to actually store this in a table. So we won't be storing this in a list. So this is going to be something that you need to practice, making sure that your calculator is doing this too. So grab a calculator, make sure that you're following along. So what I'm going to do is I'm going to put my observed into a matrix A. And so I'm going to go ahead and go matrix, and I'm going to go over to edit matrix A. And in this case, we need a matrix that is 3 by 3. Notice that I am not going to put in the totals. So I don't need to compare totals because I expected 84 and I observed 84. The totals are not part of the matrix here. We're just doing what our observations were for each of those overlapping parts. So I'm going to enter in my 30 here and then my 39, and I'm just reading that observed table. Okay, so here's my observed table. It's telling me that I have all 9 observations there. And again, I don't need the totals in this table. So then I'm going to go to my matrix again here, and I'm going to go scroll down to B because this is now where I need to get to edit. Go to B, and we want to edit matrix B to be our expected values. So again, I'm going to match that 3 by 3. If they don't match, your calculator won't run the program. And then we had our 34.22, our 30.56, our 34.22, and keep going. Okay, so now I've entered in my matrix A, observed, my matrix B, expected. Now I'm ready to go ahead and enter in, I'm going to quit. Now I'm ready to go to stat and actually perform that test. So when I opened up chi-squared test, it said, all right, what's your data? So they said, put it in matrix A, put it in matrix B, and go ahead and calculate or draw this out. So remember our chi-squared distribution is that skewed right distribution here. And that's not a lot of coloring in at all visually because we're going to reject here. We have a chi-squared that's big, 18.27, meaning we're observing some sort of difference here. And our p-value is 0.001, which also causes us to reject. All right, so when we come back here, we have 18.3 and a p-value of 0.001. So our conclusion here, because p-value equals 0.001 is less than the alpha of 0.05, we reject the claim. So what did we find here? We found convincing evidence that there is a difference. So that's our alternative. We found evidence that there is a difference in the distributions. And we'll bring back in that context the distributions of music and wine types. All right, spend some time on your conclusion. Make sure that you have that context there. One of the things that I want to show you is our calculator. And this was something that a student discovered, I think 2 years ago, that I didn't even know happened. All right, so when we did stat and tests, okay, our calculator is asking us for 2 things. So I have always done it just the way we just did. Observed, plug it in, expected, plug it in. I had a student that made a mistake and forgot to plug in their expected values. So let's pretend that we're going through it like that. If I went to edit and on matrix B, okay, if I just cleared it out. So I'm going to say, let's go 1 by 1. And I'm going to clear that out so I have nothing. Maybe I think it might have to have a 0 in there. But again, I'm just clearing it out so that you see that it is not matrix B anymore. And so I had a student that forgot to calculate his expected values, but still went and ran the test. So he went up here to chi-square test, had forgotten to put it in. He was like, oh yeah, I did that, plugged it in, and drew it out. Remember, I just took out the expected counts. I'm not sure how it's doing this. And I was like shocked. I was like, this is crazy. So I was like, well, what happened? We just deleted out that matrix, right? It's back. You saw it with your own eyes. If I look at matrix B and look, it's giving us even more decimals than what we had. I love it. This is a way that our calculator is actually programmed to find the expected values for us. So while we might be asked, what is the expected value? our calculator will actually find that for us, so we don't have to do row times column divided by table, row times column divided by table. It's tedious, and our calculator will actually do that for us. So that was a happy little accident, kind of going with the Bob Ross approach there, where we discovered that even if you don't put anything in matrix B, it will find that expected value for you and run the test. So I'll show you that on our next example. So it says, has modern technology changed the distribution of birthdays? With more babies being delivered by planned C-section, a statistics class hypothesized that the day of the week distribution for births would be different for people born after 1993 compared to people born before 1980. All right, to investigate it, they selected a random sample of people from each of both age categories and recorded the day of the week on which they were born. The results are shown in this table. There's our phrase, convincing evidence, four-step process, that the distribution of birthdays has changed? All right, so anytime we're doing a table problem here, we're going to say, is there convincing evidence that the distribution has changed? We're going to say, claim there is no difference, or it has stayed the same. So here we'll say there is no difference in the distribution of birthdays. And alternatively, okay, we suspect that maybe the 2 years, this is where they were developing the C-section, and this is after it was considered a very safe practice. So now we're going to say there is convincing evidence, or there is a difference in the distribution of birthdays. And they haven't told us at what significance level. Holy fish, that looks bad. Okay, I'm going to try alpha again. A little bit better. So at 0.05, our plan here, we have a table. We're going to do a chi-squared test. We're looking at no difference in distributions versus a difference in the distributions. So this is chi-squared test for homogeneity. And check conditions. So we have random. Okay, did they randomly select? It says they were random samples from each group. Okay, large count, 10%. We had 150. Okay, I'm guessing as far as everybody's birthday, we can definitely get, forgot my zero, 1,500 more than that in our population there. And large counts. Okay, so this is the part where I want us to use our calculator without having to go 21 times 77 divided by 150, because we'd have to do that 1, 2, 3, 7, 14 times. It's very tedious. So what I'm going to do is we're going to come back to this. This is something that we need to check. So I don't want to lose this, but we're going to go ahead and run the test here, because it will find those expected counts. So right now I'm acting under the expectation that we have met that condition, and I'm going to go ahead and find the chi-squared value and the p-value and come back to this. So it's a little bit of cheating, but I won't tell if you don't. Here we go. All right, so I'm going to go ahead. We still have to program our matrix for matrix A. So we still need to put in the observed. So now I'm going to say 2. Oh, that's not what I wanted. It's okay. I want 7 by 2. I mess with those. We go rows by columns there. All right, so I'm going to put 12 and 9. They should be the same. If there's no difference, we're thinking those two distributions here, left and right, should match. We're observing a slight difference. Is this due to sampling variation, or do we have convincing evidence that something has actually changed it? Again, do not put your totals in. We don't need the totals in our table here. All right, so here's matrix A. Again, I'm leaving matrix B to calculate by the calculator here. So we'll go ahead and run our chi-squared test. I have my observed and matrix A. I want them to calculate the expected, and we'll go ahead and draw this one out. Okay, woo, that's coloring a lot. This is telling me that this is pretty common. So we're gonna have a chi-squared that's pretty small with a high chance that it's just sampling variation. So the observations that we're seeing different from the expected is not so unusual that we should reject. So here we get a 6.55 here. And we had a p-value of about 36%. Okay, careful. This is why I highlighted it. Go back. We need to make sure and verify that all expected counts were greater than 5. Otherwise, our chi-squared and p-value are flawed. So I'm going to go back to my calculator, to my matrix, and we have to show that we've counted and figured out the expected counts here. So I just pull up matrix B and hit enter, and it's going to give me those values. So I'm going to go over here. We have to show either the table kind of over here, or you can put it in next to the chart here, but we have to show that we've considered and checked our expected counts. So you have to have them put in somewhere. And so if I put it over here, I'm going to have 10.78, 10.22. Okay, so I'm just copying that from my calculator, 11.8, 12.8, 11.3, 12.3, 9.2, and 8.7. All right, I need it a little bit bigger there. All right, then I'm matching on the other side for after 1993. Don't round all the way up to the count, but give me at least 1 decimal. Okay, so again, either here or put them right next to here in the chart, but we have to show that we've considered that all expected counts are greater than or equal to 5. That is met. Here's our expected counts. So you have to communicate to the grader, to the reader, to me, that you have created that expected counts chart. We need observed and expected. Even though our calculator will do that for us, we still have to copy it down to say, how did you check that? Otherwise, they're going to go, oh, they just wrote that down. They didn't actually consider it. All right, so once we've done that, so I think either approach is fine. Just be careful using your calculator. If you don't write that down, you do lose that point. Once we have our chi-squared and p-value, then we're ready to make our conclusion. So for this case, because p-value equals 0.36 is greater than alpha, we fail to reject. Okay, we didn't find, or we failed to find convincing evidence of a difference in the distribution of birthdays. So while that seems like it has changed, we're saying based on our data, we haven't found a convincing change in those distributions. Babies still get to make their first decision of when they enter the world. So even though there are more safe scheduled C-sections, there are still plenty of babies that are not planned as far as the day that they were going to be born. All right, so a little bit different here. Still a lot of calculator work. So if you're not practicing with me, I suggest you really pick it up and you practice entering these pieces in. Chi-squared goodness of fit has lists. Chi-squared test for homogeneity has matrices, a table. Make sure that you're able to enter that in and I can help you troubleshoot any issues you have. All right, thank you.